Welcome everybody to this talk by the Geneva Symmetry Group, Colloquium, the first one this semester. We are very happy to have as our first speaker, Luca Gasparinetti, who is a PhD student at the Università degli Studi di Milano. And he will be giving us a talk today about the temporal structure of space-time. Oh, that's not a subtitle. Yes, so please, please go ahead.
Thank you everyone for being here. I'm super happy to present this work because I think this is the perfect audience for this paper. And if you want, you can scan my paper. Yeah, basically today I'm going to talk about again the temporal structure of space-time, and my focus will be indeed on the causal theories of space-time. So let me give you a little bit of background here. I think that maybe someone knows a lot of details about it. So causal theories of space-time fell into disuse due to some criticism, and the point is that there has been some revival of this theory based on a series of theorems and to the recent developments in causal set theory, in quantum gravity, and the program of causal set theory, and this gives rise to novel causal theories of space-time. And the main difference is that spatial-temporal relations are grounded in and not identical to causal relations. In the literature, there has been proposed two different kinds of this theory, one based on causal set theory, and the other one in GR. So the core motivation, one of the core motivation, I guess, of this theory is a specific the following claim. So the structural relativistic spacetime is deemed to be causal, and more specifically, the partial order relation that is central to these theorems is best interpreted as causal. So the aim of this talk is pretty straightforward, as I will argue, I will suggest better, that this partial order relation is better interpreted as temporal, not causal. So to argue for that, this is the structure of this talk. It's pretty straightforward. In the first part, I will just go through some basic physics stuff that will focus on the causal structure of space-time, and then I will provide my philosophical analysis of it through the second part of this talk. Then I will get to some very rough conclusions and possible points for further developments. So let's start with the first part of this talk, and let's investigate what physicists says about the structure of space-time. And it's indeed the aim of this section to show how physicists conceive causation in this respect. So we can indeed proceed in two different ways, and I quote this specific paper, which is the one in which Bombelli and collaborators have provided causal set theory for the first time, like general. And we can proceed in two different ways. So from the usual way is from relativistic geometry, and from that we can recover the causal order, or we can proceed. What happened? Okay.
I'm sorry, you need to share the screen again.
Oh, okay.
Yeah. Yes.
Like
the green button on the bottom. Yeah.
That's fine, right?
This is okay.
Ooh. Okay. Good. The second way is the other way around. So, and it's the one of causal theories. So we can start from a causal order and get the relativistic geometry. So let's now consider the first route. So from the relativistic geometry to the causal order. So we can consider this very nice quotation from Bombelli and collaborators. They say, ordinarily one thinks of a spacetime as a topological manifold and go with a differentiable structure with respect to which a metric is defined. Then the causal order P is regarded as derived from the light cones of G. So let's unpack this quotation. And it's just sufficient to consider special relativity and the light cone structure as usual. So let's pick a manifold. So M is a 4D smooth manifold with a Lorentzian geometry metric. and M is simply connected, and so we can define time-orientable spacetimes. And it's important that throughout the paper, I will consider time-orientable spacetimes. And then the metric defines the Leibniz structure on this manifold. So we have like the very usual Leibniz structure. We all know that, so we can skip that. And it's important to know that we can focus on the causal relation on this slide columns. And the causal relation is defined as follows. So let Mg be a temporal oriented relativistic spacetime model, and the binary causal relation is defined as for all P in Q, and P causally precedes Q if there is a smooth future directed timeline or causal curve that runs from P to Q. So this is a 2 points, and it's very straightforward to identify the causal curve. So far so good for the first truth. Let's now consider the second truth. So again, another very nice quotation again. Given a spacetime obeying suitable smoothness and causality conditions and of dimensionality greater than 2, and that retain from all of its structure only the information embodied in the order relation P. Then we can recover from P. Oh, jeez. Should I share again? Okay. Let's recover from P, not only the topology. I don't know what's going on. Okay. But we can recover the topology, but also its differentiable structure. Someone
This
has
is
me.
not us, this is a room, I think, Flash, that the very try to control.
I don't know.
From everything, yeah, everything is like that.
Now it seems to work. Right?
Yeah, I guess.
Okay.
Yeah.
I will try to. Okay.
So.
No worries. So we can recover from P not only the topology, but also its differentiable structure and the conformal metric. So let's unpack again this definition, this quotation. Okay. This is basically based on the Hawking, King, McCarthy, Malament, Levichev theorem. So it's a bunch of theorems which can be summed up in the following way, following Surya 2019 paper. If a chronological causal bijection FD exists between two d-dimensional spacetimes, which are both future and past distinguishing, then these spacetimes are conformally isometric when d is greater than 2. So it's important to say here that the conformal metric preserves the line structure and angles between curves, but not distances, volumes, and durations. So in order to get the fully relativistic spacetime geometry, we need to also add the local volume element. So the take-home message here is okay. The causal structure together with the volume element fully determines the Lorentzian geometry of spacetime for this specific kind of spacetimes. Okay. So from this theorem, we can propose two different causal theories. So the one has been proposed in the context of continuous GR, according to which, very roughly, the continuum causal structure give rise the continuum conformal geometry via the theorem. And this is, again, it's pretty straightforward. We have causal structure plus the volume element, we got the Lorentzian geometry. And again, here the causal structure determines which events are connectable via causal paths, and this is the same relation as before. And the local volume information tells us how many events are there in the manifold region. So this causal theory of spacetime takes this metric decomposition as sufficient for an account of spacetime geometry. The second theory is very similar to this one, and but it's based on color set theory. So this is a discrete version of the one that we have saw. So the discrete causal structure is represented by underlying set, which is conjectured to approximate the entire spacetime geometry. So here the motto is a little bit different because we have order plus number approximate the Lorentzian geometry. So the order is established by the precedence relation that establish a partial order on events of the causal sets, and this relation is reflexive or irreflexive, anti-symmetric, and transitive. So we can thus avoid causal loops. Is also discrete, and C is considered to be countable. As for the local the volume, then we have the number which approximates the volume, so it tells us how many events, elementary events, are there in the causal set. And then it's important also to mention that it's assumed that there is a faithful embedding that preserves the causal structure and the local volume information. So again, if we have the causal structure, we have X precedes Y, then also in the manifold, we should also have that X precedes Y. And then we have also the local volume information. So far so good. Now let's go beyond physics and enjoy some philosophy. So the key question here is, what is the metaphysical interpretation of the partial order relation that structures space-time and causal sets? This is the main question that I'm going to deal with for the rest of the talk. So it's important to know that this is a discussed issue, but it's not yet settled, at least from the philosophical point of view. Even if it might seem trivial, because again, we saw that in the first part of the talk, we saw that we are dealing with causal notions, so it's a causal relation. But again, for philosophy, it's not that trivial, at least from my point of view. So my claim indeed is that this partial of the relation is best interpreted as temporal, as not as causal. So here we go with the second part of this talk, and let's start with the plan. So here is the three-step analysis. First of all, I will provide the temporal interpretation of this partial order relation. Then I will deal with the causal interpretation and its possible problems. And finally, I will draw a comparison between the two. So, but before going to that, a caveat and a clarification are in order. So first caveat, I will just focus on GR, and the reason can be is the following, because also causal theorists argue, or at least they clearly say that, for instance, there is already a well understood sense in which causal set theory is causal, as it involves causation in the sense of recovering the causal structure of GR. And so again, in another paper, given the tight relationship between the fundamental relation of CST and the causal structure of relativistic spacetime, we take it to be legitimate to dub this relation a causal relation. So the guiding idea of CST is to offer theory in which relativistic causation is fundamental as spacetime emergence. So again, despite formal differences, for me, it's at least for the purpose of this talk, it's fair to restrict our analysis to GR. And CST indeed can be deemed to be causal in the same sense in which GR is causal, at least as we can find in causal theorists' analysis. And yeah, we can just conclude that if GR is not causal, neither is CST, at least in this respect. Indeed, one can look at the dynamics of CST and find that, for instance, in this paper, they provided a stronger sense in which causal set theory is causal. But this is for another talk. So, and now get the clarification. So let's put on the table our task here. Our task is pretty straightforward, no? So we list the desiderata that any metaphysical interpretation of this part of the relation must satisfy. And these are just true. Whoops. So first, it induces a strict partial order as required by the theorem. And also it must capture the idea that two events are somehow connected in a way that we should expect from the Lightcon structure. So in a way, there has to be some like similarities between the Lightcon structure and this partial order. So that's it. We don't need anything more, no additional assumptions are required at this point. We just need these two desiderata. And so again, which metaphysical interpretation can we consider at this point? Which one? So if we look at the metaphysical toolbox, then we can find for space-time physics, we have like two main candidates. On the one side, we have the temporal relation. And for instance, consider the relation between the extinction of dinosaurs or whatever you want, and me writing this paper or me giving this talk, or me fixing the computer. And again, yeah. So for explanatory purposes, one can just say, okay, dinosaurs are before me, for instance. So there is no causal relation required, at least in the standard case. So temporal relation on the one side, causal relation on the other side. So for instance, consider the case in which both temporal and causal relations are required, because for instance, me throwing a rock to a window and the window shattering, there is obviously, we can say, at least again in the standard case, that both causal relation and also temporal relation are required for explanatory purposes. So we can just actually decide between these two candidates and see what's going on, what will happen. From my point of view, I think that both relations seems viable. Okay. And in order to judge, I think that it might be nice to consider a criterion to decide which one would be better. And the one that I consider here is the ontological parsimony criterion. So no, given equal explanatory power, then the interpretation with fewer, less contentious commitments is preferable. Okay. So let's start with the temporal interpretation. And actually, let's take a step back here, okay? Because in order to get to the temporal interpretation, we need to look at what I call the topological interpretation. This will be clear in a moment. So according to this interpretation, yes, you can see it. The topological, we can interpret the topological relation as this relation can be considered as a light connectivity relation with a direct topological meaning. I found this view in several works, actually, in the 70s and 80s. So, for instance, Nerlich writes, all these constructions of the causal theories of spacetime and its theorems can be indeed made on a topological basis, just as these writers say they can. But the basic relation of this topological structure is not causality. It has to be some other relation, either the elsewhere relation or the light connectible relation itself. And it's very interesting also to note that in the very same paper in which proponents of causal set theory argue for the theory, in a footnote they write, there have been also proposals in which a partial ordering has been used as a fundamental structure, but with a direct topological meaning rather than a causal one. And again, also ultimate collaborators in the paper, in the abstract, they write, the topology is more appealing, physically manageable than the topology previously proposed by Zimmer for Minkowski, so it doesn't matter. But it's interesting to note, it does seem that many calculations involving the above structure may be made purely topological. So based on this quotation, then we can consider what Nerlich actually say and develops his idea, because then he writes, one can define light cone in a completely satisfactory way by means of light connection. If we identify the light cone in its interior by means of light connection, it's not clear how this shows causality to be basic. And so from what has been written here, we can indeed say that one desideratum is fulfilled, because this guy interpreted as a light connectivity relation can capture the idea that three events are connected somehow in one aspect of the light cone structure. So this should be pretty clear. Okay, but for this interpretation, we have a problem, because the light connectivity relation is a symmetrical relation, and is also spelled out by Nerlich again. So if P lies on or is within the light cone of Q, then Q likewise lies on or is within the light cone of P. So, but we recall that we needed a partial order relation, which induces a strict partial order. And this cannot be done with a symmetrical relation, and that's why this desideratum is not fulfilled. So indeed, again, we need a partial order relation, and so we can add the temporal orientation, which is also assumed by the theorem. And from that, we can recover the temporal relation. And so the temporal interpretation, basically, one can argue that one can interpret that this partial order relation is a temporal relation. And it's interesting to know that this interpretation has been proposed in footnotes, is not being cannot be fully developed. So it might be, I thought that it might be nice to try to understand and further develop this interpretation and compare it with the causal interpretation. So, for instance, in a footnote in 2020 paper, Docker writes, in GR, the space-time causal order is a relation of precedence of before and after, not of causation. Okay. 4 years later, Butterfield and Docker writes, this use of the word causal in GR doesn't imply causation, whatever that might mean. So to say X is to the causal past of Y is merely to say that X is before Y and X is after, Y is after X. So with this, we can say that both desiderata are fulfilled. So the temporal interpretation induces a strict partial order and captures the idea of the Levichev structure. So we can draw a conclusion from this because nothing in the mathematical results forces a causal reading of this interpretation. We have recovered, I think, what we needed for interpreting right this relation. And so one can also conclude and say that the fundamental ordering relation in GR and also for CST can be considered as temporal rather than causal. Okay, so far so good. Let's now go to the causal interpretation and ask this very nice question. So why are we tend to use the notion causal? So here again, another nice quotation by Docker. She writes, the ambiguous term causal order is used because the space-time chronological relation is defined by time-like curves, and to distinguish this from the relation defined by time-like and null curves, the term causal relation is used for the lambda relation. So it might be just a pure convention, the use of notion of causal, temporal. So it's just for practical purposes, we just change the name and there's nothing to worry about it. But for causal theories, there is a genuine reason to use the word causal. And again, so let's stick to this interpretation. So the causal relation, this partial of the relation has to be interpreted as causal. But why? So let's start from relativistic causality. So as in the previous quotation by Chris, he talked about relativistic causality. So relativistic causality is basically a requirement that causal processes or signals can propagate only within the light cone. So we can, Norton summarize this, describe this constraint with the slogan, no propagation outside the light cone. I think that here the use propagation, it seems to lead us to attempting a causal interpretation, because propagation can be regarded as an influence and something that causes something, if we endorse, for instance, the productive account of causation. And we can thus rewrite the slogan as no causation outside the light cone, which I think should be fair reading. But in any case, both these data are fulfilled because the causal relation induces a strict partial order, and that's fine. And also it captures the idea that three events are connected in a way one expects from the light cone structure, because for this reason. Let me mention a caveat here, because in several papers, causal theorists explicitly write that this is not the much richer of the causal relation. So it's not the usual relation that we find in everyday case scenarios. And importantly, we don't attribute causal efficacy to all time-like or null relations, because only some of them are real instances of causation, actual causation, and others are just mere possible instances. So that's why we should call it causal connectibility, like Van Frassen, who endorses specific view, causal theory view. Okay, here is a reply from causal theorists, but this interjection is neither very insightful nor is it at all damaging. Those moved by it are hereby invited to mentally replace our talk of causation with a more precise but also more awkward substitution in terms of possibly directed causal connectibility. So it's important here there is a clear sense in which the causal structure of GR is fundamentally primarily causal and only derivatively temporal, as it encodes relation of causal connectibility of events by light signals. The reason why this is basically the Malament theorem. Again, it can be shown that important results, such as Malament theorem, are closely intertwined with the history of causal theories of time. This theory inverts the usual metaphysical hierarchy between time and causation and assume that causation is the more fundamental of the two. So, to wrap things up, okay. So it's thanks to this theorem that the partial order relation can be deemed to be causal in GR and also in causal set theory, as it captures the idea of causal connectibility of events. And again, a temporal theorist like Docker can claim that this relation is a temporal relation or an order of before and after, not of causation. But why causal and not temporal? Because temporal relation is supposed to emerge from causal ones. We are supposed to explain space-time, so to recover space-time from something that is not spatio-temporal. That's the toss, I guess. And so this theorem shows that causal relations are fundamental. So let me now put on the table two different problems for this causal interpretation. So the first one is that I think that modality here is not needed. So again, we said that this is a weaker notion of causation, and we can call it causal connectibility. It's not actual causation. And it's important now to make little clarification, because here causal connectibility, as used in Van Frassen, for instance, is a binary reflexive and symmetric relation among events. But clearly, this is not what we have in mind, what we're dealing with the Malament theorem, because again, this relation has to induce a partial order. And also it's a model relation. So again, it's not true that all events in the past, future, lexicon are events of an event are causes / effects. So what we should look at it is causal connectivity relation as an irreflexive, anti-symmetric, and transitive model relation. That should be our focus here. So it's important for me to note that first, formally speaking, the theorem relies again on an actual causal precedence relation. I mean, there is nothing in the theorem that appeals to the modal nature attribute to the relation by causal theorists. And from my point of view, I think that causal theorists have to assume that this relation is modal. Otherwise, it would result in an appropriate interpretation. Why so? Because not all future events of P are causally connected. So they, in order to make the interpretation work, they have to assume the modality. And again, because the modal operation here is not required, so it's required to avoid ascribing causal connection when actually they are not. And this is important because for the temporal interpretation, so the temporal theorist, it seems to doesn't face this problem, because all events lying in the future cone of a point are temporally related to it. So it's, just to make a very stupid example, what is true that dinosaurs are temporally connected to me, it's not true that the latter event is causally connected to the former. At least if you want to say that it's true, then you have to like say something more about this story. But again, I know that from an intuitive point of view is not that appealing, but you have, if you want to say that it's true that the latter event is causally connected to the former, then you have to provide some history on that. So they have to provide some philosophical analysis. So my conclusion is that the model operator actually represents a constraint imposed by causal theories that is needed to adjust the causal interpretation. But this guy is not needed for the temporal interpretation. So this is a cost in order to endorse the causal theory, the causal interpretation. So the second problem actually is not a problem, but a difficulty in a way, because it seems that we have no fit with standard metaphysical accounts of causation. So we can think this relation in terms of production theorists like process theories. So causation is a transference of a certain quantity. And one can say, okay, let's try to interpret this relation in these terms. But the problem is that they also highlighted by early. The idea of a process like sending a signal of particles or whatever you want goes beyond the structured space-time. I mean, it appeals to the dynamics, not the kinematics. So one can also say, okay, let's look to dispositionalism, for instance. And I don't know, according to dispositionalist, space-time is a dynamical entity, whose causal powers affect the motion of different bodies. So one can try to interpret this relation in dispositionalist terms. But again, it seems like, again, there is some work to do in this way. And we can consider, for instance, Libanius, who argues that space-time metrical structure doesn't causally affect material bodies, it just determines which paths are available to bodies when moving inertially. So it seems like the causal torque in this case is not so big. On the one side, production theories, we can also consider like dependence theories of causation. And one is, for instance, interventionists, which is a special case of a specific version of the counterfactual theory. And here, causal relation should support the possibility of intervention. So one event can causally influence another. The problem with counterfactuals in this case is that in GR these counterfactuals are ill-defined and has been noted in the literature. So one can just say, okay, I don't want to go reductionist theories of causation. I'm a primitivist, and yeah, I'm a primitivist. Oh, sorry, but let's do here. Never mind. Let's take a step back. So for reductionist theories, it seems to me that this partial order relation seems insufficient to cope with reductionist account of causation, as it seems that they require more. So obviously, I'm not making the point that this cannot be done. For instance, in a paper that has been proposed, a non-spatio-temporal interpretation of the interventionist account. So we can use like non-standard approaches to do the job. But again, if we invoke causal relation, then this might create the difficulty in understanding what causation is. So it begs the question. So we need to answer this question: what is causation? And again, move forward. We can say, okay, I'm not a reductionist theory of causation. I'm a primitivist. We can consider causation as a primitive relation. Fair enough. That's fine with me. But I think that is not preferable to adopt the causal interpretation for the following reason. Because if you are forced to say, no, I'm a primitivist, then causal theorists have to commit to a particular view in the causal reductionism versus causal anti-reductionist debate. And I think this is not preferable because, for instance, if we just go in temporal, we can remain this dispute, and we just say, okay, let's deal with B-theoretic, specific version of the B-theoretic temporal relation before and after. Nothing strange. I don't have to do some commit to a specific to a specific debate, to a specific view, so I can be neutral and go in temporal. I think it might be easier. So let's now draw a comparison between the two interpretation. So on the one side, we have the temporal interpretation, on the other side, the causal interpretation. So is the time?
No, we have 10 minutes.
Okay, great, perfect. I move faster, so I will finish a little bit early. So on the one side, we can say that for as far as the explanatory power is considered, we saw that both interpretations seems to fulfill the desiderata required. So they both induces a strict partial order, and also they can account for the light cone structure. So they gives a way to recover the light cone structure. But the temporal interpretation does that without the cost of modality, because again, we can just say that all events in the future past light cone are temporally connected to a specific event. But the causal interpretation by contrast have to assume some sort of modality. Otherwise, it seems to doesn't work, because not all events are causally related to a specific in the light cone, or on the edge of the light cone are causally connected to a specific point. And the second cost for causal theorists is that we put a constraint on our okay. If you appeal to the ontological parsimony criterion, so given the same explanatory power, the interpretation with fewer and less commitments is preferable, then I can conclude the following. I can suggest the following conclusion, that the temporal interpretation is preferable if we accept this analysis. So let's now get to the conclusion. So first of all, we can say that relativistic causality has to be interpreted as just a technical term used by physicists that should not be confused with the philosophical term of causation. So we can put a difference between causality and causation, just for the sake of clarity. And so relativistic causality is a constraint on a partial order relation. And I think that by putting a difference between relativistic causality and causation, that this should be better spelled out. And it's important to know that, as also suggested by Nerlich in the same paper that I quoted before, that this series of theorems doesn't show that this relation is causal. It just shows that a generic partial order relation does the job required. And again, based on my analysis, I think that the relation is best interpreted as temporal. And so this can have different, so if we accept that this is the best interpretation, then it seems that we can draw some very interesting conclusions. One concerning, for instance, the debate on fundamental causation, as it seems that causal set theory makes the case for fundamental causation, but if we look from the point of view of the temporal interpretation, then it seems that there is no fundamental causation. There is just a proto-temporal relation that does the job required. And this is for one debate. Then the second debate, one can argue, for instance, that causal set theory makes the case for causation without time. In light of this reading, one can just say this is what can be like a quietist view, in which this debate is not really serious, as according to this interpretation, there is no fundamental causation, so there is just time. And finally, one can also argue, but I'm not arguing for that, I'm just suggesting this possible conclusion that space-time actually is not emergent 100%, or let's say, but we can say that there is a fundamental temporal structure from which space-time might emerge, but then it seems strange to say that emerged from a temporal structure because, or reduces to a temporal structure because, again, if we endorse, for instance, a notion of reduction, then it makes, in order to have like an ontological reduction, we cannot say that at a fundamental level we have time, and at the not fundamental level we have still like some version of time, like kind of time. So again, it seems that we can be quietist also on the space-time emergence debate. So thank you very much. And again, if you want to scan the paper, as I see here.
Right, perfectly in time. So
Right.
we have a bit more than half an hour of discussion. We can go. Perfect. Yes.
Thank you. Thank you. So, yeah, so I think from the last time I heard you talking about this, you announced a bit the also the part about the model cost.
That's completely
Yeah,
yeah.
right. And I think also maybe talking with you maybe also pressed you a little bit going towards that, but now I was wondering what is exactly the cost? Because so if you have say so tell me if I got your point. You say we have two space-time points, and these things are obviously or events, and these things are obviously actually temporarily ordered somehow. But if I want to make that order supervene on causal relation, sometimes that relation is modal, and so I want to be actually temporary order. I have to just recur to time and not only to play causes, because if not, they will just be modally possibly temporary ordered and not actually temporary order, right? Is that
Yeah,
okay?
we can say that, yes.
So the point is, if I think that temporal order supervene on causal order, why can I say just so? For instance, I could say, well, yeah, if we take a word line, the proper time on that word line, say these events are only possibly causally ordered on this word line, then they are only possibly temporary order. And the proper time is just, you know, possible time that will elapse if two events were to happen on those space-time points. So do you think that that move is available for those who think that?
I mean, if you start from the light cone and just say, okay, pick one event, then you can like construct the light cone on this, then you can be sure 100% that the future events and the past events are temporally connected to it. So since I'm dealing with this reconstruction theorem, then it's like you are trying to reconstruct space-time, no? So, and my idea is that you should be not consider more commitments than you should expect. So you can start from, I mean, time, we all know that time in a way is less constrained by causation, because if you want to talk about causation, especially also, for instance, in everyday science talk like economics, science, then you have to add like a very clear explanation of why you are dealing with causation. Otherwise, it's just correlation. So if we turn this into physics, I would just say, okay, we can start with this theorem. We have like this relation order events. And then if you want to like add like a causal description of this, I mean, that works, because I mean, to be sure, to be clear, I seems that both theories, both interpretations are available. So I'm not like saying this is the worst one, we should not. But I think that in a way, there might be less commitments if we just consider the time interpretation, because at the end of the day, you pick a point, you know that future and past events for sure are temporally related. But then if you want to,
Yeah, sorry, but so
maybe I'm not answering the question.
just to try for clarification.
Yeah.
You take two events
Yeah.
as actually occurring, right? They are actual events.
Yeah, okay.
Okay. And you say these events are surely temporally related.
Yeah.
But then they are also causally actually related, right? Because why would the causal relation in that case? So for how I understood you, the causal relation is modeled when the events are only possible and not actual.
No, the point is that, okay, you can pick an actual event, like I was discussing. Okay, and for instance, you construct on me the light cone and look at the possible future events. But then there might be some actual causal connection between my point and the future events. But at the end of the day, if everything is actual, then you should ascribe causal connection only to some points, not all of them.
Okay.
That's why I think that if you are committed to the causal interpretation, then you should ab initio, you should consider this model commitment. Otherwise, you will end up with some events that are not causally connected, and this is wrong. As far as
Understood. Rico.
Yeah, thank you. This was nice. Maybe let me start from just the broader point, which is that it seems to me that what the paper shows is that causal structure should not be identified with specific instances of causal relations. So that basically you should not think that causal structure fixes your token causal relations, which seems like a very fair thing to point out. I'm kind of confused as to then why we make the jump to temporal structure or to the fact that this has nothing to do with causality. In the following sense, that if I tell someone that my theory has among its properties the property of being local, so that I don't know, space-like separated operators commute, for example, they will probably think that I'm telling them something about causal relations. And you signal this because this is called the causality condition, not the temporality condition. Now, if from that they derive the claim that locality is sufficient somehow to determine the specific token causal relations that obtain in a model of my theory, of course, that would be a very strange thing to be. I have no idea why you want to believe that. But that doesn't remove the fact that that condition is a condition about causality. So that then whatever relations I have, whatever thing I use to enforce this type of conditions is best thought as being at least part of the defining of the causal relations in my theory. Then maybe there is some more stuff that I need to add. And undoubtedly, I'm not the right person to ask about causal set theory. So I won't try to say they do anything more than that. But like the fact itself that the causal structure, what Malament uses in his theorem, is not sufficient to define the token level causation, doesn't strike me as implying that, well, then all of a sudden we shouldn't think of those as that partial order that Malament uses as causal or as part of what defines that token level causal properties. You could think of it as a way, for example, to define something at least part of the type level definition of causal relations. You could say that there is a type causation, which among other things has these properties encoded by the partial order relation that Malament uses. And then there is some further stuff at the token level that needs to be fixed to speak out a specific sequence of tokens. But then you wouldn't use time at any point in this story.
let me see if I got it everything. So let's go back here. Oh no, I can't. Maybe can I? Oh yes. Okay. Yeah. So what I'm just saying is that one, no? So here we are So keep in mind also Docker quotation on the light construction and why you should talk about just why people talk about causal notions, no? So you have here, my main idea is that, which is perfectly aligned with learning. So you have a point, this curve, so forget of this like specification, no? So you have time space, remove the word causal, and you can just use time like hers. And people, what they're doing is that in order to differentiate points from this region to this region, which is the null like right? We need to include the word causation or whatever, because I mean, for me, you include just the word causation because it's for the relativistic causality conditions. For me, it's perfectly fine to call it relativistic causality. Also, spacetime has like several causality conditions, like a globally hyperbolic or stable causality and so on. But the point is that why I can call it, I don't know, Giovanni curve, and then I mean, for me, it's just a way to differentiate these points from these points that you call then, and then to like summing up these points with this point that you call it causal. But then in order to reconstruct the theorem and reconstruct everything that you want from the theorem, then you don't need actually the word causation for doing that. So I don't know if I like answer to your question.
You need the word causation in the sense that the theorem is a piece of mathematics. And so you don't need any more. But
Yeah.
The reason why you
We can say that.
the reason why it's called a causal relation is
Yeah.
because, and not anything else, is because the causal structure, which is the thing defined in terms of that relation, is it tells you which points can interact and which points cannot.
Exactly.
That's the point.
That's
Interaction is a causal concept. That's why it's
Exactly.
called causal structure. Now, what's happening is that these notions are kinematical notions, which means that in general, they don't tell you which specific points are causally connected. Just puts constraints on that. The problem is that most of the philosophical literature on causations, strangely enough, is concerned with something else. It's concerned with token level causation, which is what Lewis does when he talks about kind of factual theories of causation. It's token level causation. This stuff is not token level causation. It's closer to, I don't know, type level causation.
Exactly.
In some sense. This doesn't mean that it's not causation that's happening here. It's just that you need to, and it's a fair point to say that you need to actually do some extra work to explain the sense in which these type level constraints then are related to the type of to the token level causal relations, causal processes that people like Lewis talk about. But what I'm contesting is that one should just make this observation and then jump to the conclusion that, well, then these causal structures nothing to do with the causality conditions, whatever we want to call them, are not causal. They have to do with time or other properties. They are causal in some clear sense. It's just that there's this strange mismatch.
Can I just reply then? Thank you.
I have a thing. Yes.
Okay. You talk about constraint, and I mean there has been some people that interpret like this causal structure as like causation as just a constraint. So there's nothing to do with like causation in the usual sense. It's just a constraint on that. And for me, I'm perfectly fine for with this reading, because again, relativistic causality is not that it doesn't talk about like causal relation. It's just talk about a constraint on some kind of relation. So I think that's a fair reading. So if you like interpreting causation as a constraint instead of an actual relation or type level, token level, you can just say, fine, you have a relativistic causality constraint on a partial order relation, and this does the job required on this reading.
I wanted to react to what was on your last slide.
Yeah.
That's sort of a similar point connected to what Enrico said.
Yeah.
So Enrico said we need a physical interpretation of what we're doing in the mathematical theorem. I completely agree with that. So it's not just any partial order relation. It is a partial order relation which has a physical interpretation. That's why physicists care about it, and not just mathematicians. It cannot be one of interaction, which is, I suppose, a symmetric relation again. So it must be something slightly different, and I propose it would be something of, a light signal.
Yeah.
So it's a binary relation between 2 points, from the first of which a light signal can be sent to the second. Sort of, it is a form of interaction, a very specific form. Even though it's not a two-way interaction, it's a one-way action, maybe one-way interaction or something like that. And that's what I think the correct intended physical interpretation of that relation is. Back in the 70s when Malament and Hall came and were worried about these things, I think as such, it's not directly and immediately connected to any of our sort of more common conceptions of time and causation. To show such a connection requires much more work than any of that. It really just is that, in a space-time, you can send a light signal from A to B.
Yeah. I mean, that is a fair reconstruction on everything. And I was wondering why, while I was reading the paper and the book from Van Frassen, and I asked myself, why the causal theory of space-time is so appealing, no? And people talk about because it gives you like a physical sense on how we construct space-time instead of using temporal notions, which are like strange. We don't know what time is, we don't know how things works in this way. So we can actually use a more physical sense in which we can recover space-time. And that's and I realized that is like the main point of going causal theory in this way. But again, I mean, it depends on how you read causation, no? Because you said, okay, I send a signal, but I mean, in the theorem, I'm not using signals, I'm not using process, I'm not appealing to this kind of.
That's true, but I mean, once I've set up my initial assumptions, I just prove a theorem. That's just mathematics.
Yeah, that's fair, but
so there it doesn't really make any difference what these things mean.
Yeah, but you're trying to recover space-time, then you're appealing to a notion of process, sending a process from a certain location to another location, then it seems like, okay, maybe you can say, oh no, this makes the case for a non-spatial temporal notion of causation, of sending a process. But I mean, why should I be committed to that kind of reading while I can be just stick to a temporal interpretation plus a constraint on that, and then I can.
Because I think the worry is that the temporal interpretation brings much more with it than just this very minimal structure in a way. Times have a lot more structure, they have duration. And
yeah, exactly. But indeed, it's not, sorry if I interrupt you, but it's not like a fully fledged temporal interpretation, but it's like a time in this case is like without duration, is like a very proto-temporal aspect of the reality. It's not like a full-fledged temporal interpretation with duration. Yeah, it has an arrow of time, because it's space-time feature distinguished. But again, it's not like the super general that we should expect at a more a less fundamental level.
Thanks, that's very interesting. A few, well, I'm going to focus on one. So I think the dialectic is a bit misleading about the relation between
relativity and causal set theory.
Mhm.
And there is an obvious fix. If you want to be lazy, you just don't talk about causal set theory at all. In the talk, you filter out everything related to causal set theory.
Yeah.
I think that would fix some issue. And the issue I have is that you basically said that the situation was the same in GR and causal set theory. And I think that's not true for a few reasons. So fair enough. I mean, CSP was motivated by the Malament theorem. That's kind of suggestive, but still, at least prima facie, the relativity seems not to be causal, as you said, but in a strong sense.
Yeah.
And also, at least prima facie, CST seems to be causal in a stronger sense. So somewhere like this paper where we use interventionists to try to show that how CST is different from GR, but
Yes.
very intuitively, you take a GR spacetime, you can remove a point and keep everything
Yeah,
the
it
same.
talked to me about this. So
But if you wipe out the CST element in a model, you are going to wipe out a lot more dynamically connected. So I mean, in a way, the difference is this: for CST, you have dynamical laws, dynamical rules connecting the elements.
Mhm.
So it's a bit different. Or at least prima facie, CST seems more causal than GR. So if you wanted to also argue for the temporal interpretation in the case of CST, you will have to provide a lot of arguments, and you will have a lot more work to do in the case of CST. So you cannot just assume that what you are saying about GR will translate to CST.
yeah, thanks for the comment. Exactly, because to remember, I know it's here. Sorry. Yes, here. So I specified this because I showed you with the references that I quoted, that again there is, and in the paper that you have written with Sam, there are two different senses, not like a weaker sense and a stronger sense. So what I'm arguing here is just against the weaker sense, and this is just based on, for instance, in this quotation. So I found in the literature that a lot of literature actually say explicitly that there are at least this sense in which the fundamental relation, the causal structure, so there is like they are super similar. Also, formally speaking, they are similar because the induces a strict partial order, they're irreflexive, antisymmetric, and transitive. So formally speaking, they are the same. And also for this reason, so I'm just committed to this idea because I found in the literature that people working on this are actually arguing for this kind of resemblance within the two cases. But again, if I'm getting in trouble by collapsing the two cases, I can just focus on GR, because I mean, this is like the first step of a project in which I should like do a step forward and try to temporally interpret the growth outcome in the causal sets. In which I mean, but this is a work in progress. I'm not already thought about it.
But I mean, if you don't have this story yet to give, at least, sorry, if you don't have this story to give yet, I think it's safer not to mention that, because again, it's very different. I mean, you say it's formally the same, but as Chris said, you need to interpret the relation of partial order, and the context of GR and CST are very different, as I mentioned, because of the fact that in the case of CST, you have dynamical rules.
Yeah.
Operating directly with those partial order relations. So that makes a difference. And also, think about it like this: if you really take space and imagine seriously, you might have all the view where something like akin to your temporal interpretation of GR is correct, but still it's not really. We're not getting to the bottom of things because this theory is effective and emerged from something more fundamental. And there, at this more fundamental level, we do have a causal theory of because we are positing fundamental causal relations there.
Yeah,
But and so then, in a way, the temporal interpretation would be part of the approximation.
Yes.
Of the
Yeah.
Still be a causal theory of space, and the sense that the more fundamental level of causal relation will be grounding this GR stuff.
Yeah, yeah, thank you also for the suggestion to not focusing on CST. But I mean, I read your paper with Sam, and for now, I just have some concerns about the assumption because you have to interpret the growth seriously because it's a real process. But then, I don't know, I'm just thinking about it, and yeah, there might be some work to be done in order to maybe give a temporal interpretation instead of causal interpretation. So yeah, I will work on it, and if you want to chat about it more, I will be super happy. Thank you.
Yes.
Yeah, sorry, just to clarify, I think the position of Rasmus and me is that we don't endorse the causal reading of GR.
Yeah.
We just set it up dialectically in the context of engaging.
Yeah. That's true.
So it's not please then.
Yeah.
It's just to say. Yeah. Otherwise, we had a lot of discussion already about the semantics, what to call, okay, not maybe about causation, but causal structure and I don't know, call it connectability or what have you, right? And isn't it just fair to say that there's a long tradition already in physics now, I mean, since Rob pleased to look at some structure in space-time context, which is not spatio-temporal, but somehow more coarse, which somehow is about interactions or connectability, right? That's kind of what's now a causal structure, right? And then, so to speak, nowadays, after 100 years, as natural philosophers, this is our natural philosophical notion of causation in this context of physics, and so anyway, and this is kind of what analytic philosophers look at. This is not the philosopher's notion of causation. This is really, this is more like a semantic point. This is really just like different notions of causation for different contexts, but very remote from physics. So I'm just wondering, who is in the position to justify what, right? Who has to kind of clarify or justify him or herself for using the word causal, right? Is it really this natural philosopher side, or is it not after all? I mean, especially in their own context, so to speak, of space-time. Why isn't it the other side? Isn't it the analytic philosophers that have to justify why ever we should think their notion of causation is somewhat relevant here in the realm of physics? I'm just wondering, just a semantic point, right? But,
Yeah, it could be. But then and the main problem is that if you consider this as a melting point, then I don't know, because this is like a general issue for how to do actual philosophy of physics, no? I think. And then, at least as far as I'm concerned, so I will just say, okay, physicists talk about causation, but then, okay, so philosophers should not consider this talk like super seriously at the first time and the first sight, but then has to analyze and see, okay, can we do some work? Can we justify actually this interpretation? Can we justify the use of causation? Because otherwise, what is the work for philosophers? There is no work, because I mean, one part of the work is like to analyze what people are saying, no?
Right.
Otherwise, I mean.
Right, there's a big difference between coming with your own concepts and kind of forcing them onto, rather than getting the concept out of the physical context, right?
Yeah, but sorry.
Yeah.
For instance, Faye Docker is a physicist.
Sure.
She talk about time instead of causation.
Right.
So then there's a tension between the physics community itself. No, maybe it's just one person in the entire world that talk about time.
Yeah.
But again, it seems like there is some kind of philosophical inclination on what she is writing, and so I mean there might be like some room for philosophy here, and why this.
But also with time, you could wonder, like, right? Is this the same thing that people talk about in one developed community? How much can you really force one to talk like the others, and so on and so forth? So Yeah, just one, yeah.
No, but yeah, that's a very nice and interesting question. Thank you.
Thank you. I'm not quite sure if it's clarificatory or what, but this is a bit outside of my usual. I'm trying to evaluate the reason why you are sort of saying we don't need the causal structure relation is because it comes with all of this extra baggage. And I'm trying to evaluate to what extent that is actually a problem. So one of the things was this modal claims that the causal connectedness, but we don't have causation between actions at these points. So there must be something cutting a bit deeper here, and we can just rely on the temporal structure. And now I'm just wondering if I take a step back and sort of try to look at the whole GI structure and what I'm trying to capture. I'm not just interested maybe in recovering the space-time structure. I also want to cover all kinds of other things. For instance, explaining why some things are causally related or not. And there I was wondering whether the modal structure or like the extra baggage that we get with the causal relations also gives us a bit more flexibility when we want to look at the bigger picture. And in connection with that, then I was thinking potentially related to Baptiste's second point. Again, in causal theory, I'm outside of my comfort zone, but there, as far as I understand, is we can have causation and we don't need a sense of time to begin with. And I'm wondering if it's the same thing in GR case. If I fix all the causal structure, I don't need to also impose this temporal notion, so I can sort of, when I get a little bit further, I want to talk more just about the structure. Then I just have these causal relations that do all of this job, and I don't really need to talk about time in that sense.
Yeah.
So my question is sort of, how does this cost fit into the bigger picture? I'm sorry if I said something really confusing.
No, thank you. Let me put it this way. Let's try and put it this way. So, for instance, I pick a rock and throw the rock through the window. Okay. Then, if you want to explain this scenario, then you can just say, okay, you are recovering. So you start with just time, no? You say, okay, this event causally, temporally precedes the other event. So, for explanatory purposes, you have this kind of explanation. Then if you want like some more, then you add like the causal notion. So you say that there is some quantity that has been from one event to another. Strange, but anyway. And so the same case for the same case also for the theorem, I guess, because if you start with just like time, so you have just a partial order relation. If you interpret it as time, then you have everything that you need, basically. But then if you want to say more in GR case or whatever case you want, then you can ask an additional question. But I think that the additional question is not related to the theorem, I guess. It's just an additional question that you want to ask. But again, it's not for the theorem, it's just time. I think it's just sufficient for that. So, but then again, if you want to ask something about which event is influencing another event or whatever causally stuff, whatever you want, then it's another thing. So it's like we have two different levels